Good afternoon, everyone. So, in this lecture, we'll be starting with the gravitational field intensity, and we will be also calculating acceleration due to gravity at some height from the surface of Earth and at some depth, right, from the surface of Earth. So, we'll be discussing different scenarios of the acceleration due to gravity, right, due to Earth, right. Now, starting with the gravitational field intensity, right. So, gravitational field intensity, it's actually the region around a mass, right, where gravitational effects are observed, right? Or we can say the gravitational field is experienced by another mass m, right? So it's a region around a mass around which the gravitational effects are observed, right? And the gravitational field, we know gravitational field is a long range force, right? Or long range field, right? The gravitational field intensity extends to infinity, right? It's a long range field, right? So its intensity decreases as we move away from the mass, right? The intensity of the gravitational field decreases, right? And we assume that at infinite or distance or at infinity, the gravitational field intensity tends to zero, right? And the gravitational field depends upon the mass of a body as well, right? Greater the mass of a body, greater will be the field intensity, gravitational field intensity because of the mass, right? So let's suppose that this is the mass m, right? This is the mass m. Then the region around this mass m, around the region of this mass m, if we place any other mass m1, this is mass m1, any other mass m2, right? This mass m2 separated by some distance r, right, will experience a gravitational force or gravitational field, right? So this region around this mass m1 will be called as gravitational field, or and the intensity, or we can say the force experienced by unit mass m2, right? Per unit mass, that will be equal to the gravitational field intensity, right? Gravitational field intensity is once again a conservative field, right, in nature, right? So there are actually the two ways to calculate the strength of a gravitational field. One way is to calculate the gravitational field intensity, another way is to calculate the gravitational potential, right? So first of all, we'll be calculating the gravitational field intensity due to different mass distributions, right? We'll be discussing about the sphere, we'll be discussing about the point mass. Then later on, we'll be discussing about the potential as well, right? So there are two ways to actually know the intensity, or we can say the strength of gravitational field. One is the gravitational field intensity, another is the gravitational potential, right? Now let's see how actually the gravitational field intensity varies for the point mass, right? The gravitational force exerted on a unit mass placed in a gravitational field, that's what we call as gravitational field intensity, right? Now let's suppose a mass, we are placing a mass m, right? Mass m, it's a point mass, right? It's a point mass m. Now we have to calculate, because of this point mass m, at some point p, right? At some point p at a distance of r from point mass m, we have to calculate the gravitational field intensity. Let's represent this intensity, gravitational field intensity, by I, right? So I is the representation of this gravitational field intensity, and we know that gravitational force is an attractive force in nature, right? It's always attractive in nature. So gravitational field, when we place any mass m or any unit mass near this point p or at this point p around this mass m, right? So it will also experience a attractive force, right? Or we can say the gravitational field intensity will be attractive in nature here. So, or we can say its direction will be towards the mass itself, right? So this is the gravitational field intensity I, because of this point mass m, its direction will be towards the point mass, right? Now the position vector of this point P from m to P, that's r, denoted by r vector, right? That's denoted by r vector. Then the gravitational field intensity, because of this point mass, will be given as, it will be gm upon r square, right? Gm upon r square. Now the direction of this gravitational field intensity will be towards this mass, or we can represent it by a unit vector of minus r cap, right? Minus r cap. So the minus sign here signifies actually the attractive nature of this gravitational force. So the intensity here will be gm upon r square with the direction of minus r cap, right? So this is the gravitational field intensity due to point mass, right? Due to point mass. The direction of field intensity, gravitational field intensity is always towards the mass, right? Because of its attractive nature, right? Now let's try to find the field intensity, net field intensity at point O, right? There are 2 point mass, each of one is of mass m, another is mass of 2m, right? Which are separated by a distance of r and r from the center O, right? Now we have to calculate the net gravitational field intensity at point O. Now the net gravitational field intensity at point O, one will be because of mass m, another will be because of mass 2m, right? So because of mass m, it will be towards itself, right? And it will be because of 2m, it will be towards itself, right? So these will be the two field intensities, right? The resultant of them will be actually the subtraction of the total field intensity, right? So let me call this as I1 and let me call this as I2. So the net intensity at point O will be I2 minus I1, right? Because they are opposite in direction, right? So it will be I2 minus I1. So the net field intensity will be twice Gm upon R square minus Gm upon R square, right? That will be equal to Gm upon R square, right? And it will be directed towards the mass 2m, right? So this will be the net direction of the final direction or the resultant direction of the field intensity at point O, right? So this is the gravitational field intensity due to point masses, right? Now let's try to calculate the gravitational field intensity due to sphere, right? Due to sphere. Now we can calculate the field intensity due to sphere at its surface and at inside the sphere and outside the sphere as well, right? Now you can see here there's a sphere, right? There's a sphere of mass m. Let's suppose the sphere of mass m and radius of the sphere is r, right? It's a uniform mass, right? Or it's a uniform sphere, or we can say the mass is uniformly distributed in this sphere, right? So mass is m, radius is r. We have to calculate the field intensity. Now the field intensity of this sphere on its surface will be the same as that of the point mass, right? It will be same as that of the point mass. We know the field intensity because of point mass is gm by r square, right? Now the field intensity on the surface and outside the surface on this sphere will be the same as that of a point mass, right? So inside on the surface and outside the surface, field intensity of sphere will be same as that of point mass. Point mass, right? Now you can see this is a sphere of mass capital M and radius r, right? Now on the surface, or we can say the case first is on surface, right? The intensity will be same as that of point mass. So I will be equal to Gm upon r square. So this is the field intensity, and the direction of this intensity, field intensity, because of this mass m, will be towards the center of the sphere, right? It will be towards the center of the sphere. It will be directed radially towards the center of the sphere on the surface, right? And at each and every point on the surface, the field intensity will be same, right? For this uniform sphere, right? So Gm by r square will be the intensity on the surface, right? Now let's talk about the intensity at some point outside the surface, right? At a distance of small r, right? At a distance of small r. Let's suppose this is the point P. At this point P, we have to find the intensity due to the sphere, right? Gravitational field intensity. Now outside sphere, right? Outside sphere. Once again, the intensity will be because of the point mass, right? It will be same as that of the point mass, right? Gm. So we'll be treating sphere here as a point, right? So it will be Gm by r square, distance square. So distance will be taken from the center of the sphere, right? So the distance here from the center to this point P is small r. So it will be Gm upon small r square, right? This will be the field intensity. of this sphere, right, due to this sphere at outside point. Now talking about the field intensity inside the sphere, right, inside the sphere. Talking about the field intensity inside the sphere, right. Now what we can do is that, let's suppose we have this is the sphere, right? This is the sphere, and at some point inside the sphere we have to calculate the field intensity, right? Let's suppose at some point P, right, from the center of the sphere we have to calculate the field intensity, right? We have to calculate the field intensity. Let's suppose the distance of this point P from the center of the sphere is small r, right? It is small r, right? Now it means that if we place a mass m, right, at this point P, it will experience some gravitational force, right? It will experience some gravitational force, and the total mass of this sphere is m, right? And the radius of this sphere is capital R, right? Now it will experience some gravitational force, right? Then the mass of this portion of sphere will be, we know it's a uniform density sphere, right? Sphere has uniform density. We can calculate the mass of this portion of the sphere, right? So the mass of this portion of this sphere will be m upon the total volume is 4 upon 3 pi r cube, right? That, let's suppose the mass of this small portion of this sphere is m dash, right? It will be 4 by 3 pi small r cube, right? Now this 4 by 3 pi, 4 by 3 pi will get cancelled. So from here m dash will be equal to m times small r cube upon capital R cube, right? So this is the value of the mass, right? Then the force experienced by this point mass m at this point P will be given by the Newton's law of gravitation. That will be F is equal to G m, m here is m dash, and m upon r square, right? This will be the gravitational force. Now replacing the value of m dash, that will be m r cube upon r cube, right? M r cube upon r cube, right? Divided by r square, right? Multiplied by this mass m, right? So we'll be left with Gm, right? Multiplied by r upon r cube and multiplied by the small mass m, right? So mass is the m, small m is the mass of the particle which is placed at P, right? Now I have to calculate the gravitational field intensity. Now the force experienced by this mass m, or we can say the force experienced by the unit mass m, per unit mass, that will be the field intensity at this point P. So F upon m will be equal to Gm into r upon r cube. So this is the gravitational field intensity at the inside point, right? This is the gravitational field intensity at the inside point of sphere, right? Inside the sphere, right? This is the net field intensity inside the sphere, right? For this uniformly distributed mass in this sphere, right? So Gm r upon r cube, right? Now you can see here inside the sphere, the field intensity is proportional to the distance r of this point from the center of the sphere, right? Now if we plot this field intensity, right, versus the distance r for this sphere, so this intensity I, field intensity I versus r, right? Now inside the sphere, the field intensity is proportional to the distance r from the center. So it will be a straight line till it reaches the surface, right? Till it reaches the surface, right? And on the surface, at the surface, the field intensity is maximum, right? Field intensity is maximum. Then what happens is that the field intensity varies as 1 by r square, right? 1 by r square. So this will be the variation. Here the I is proportional to r, right? And here the I is proportional to 1 by r square, right? And this is the point where the field intensity is maximum. That's the surface of sphere, right? That's r is equal to capital R. The field intensity here is maximum with value Gm by capital R square, right? Gm by capital R square. So this is the variation of the field intensity for sphere on the surface of the sphere, inside the sphere and outside the sphere, right? This is how you can calculate the field intensity due to sphere, right? Inside, outside, and any point. At any point, right? Provided it's a uniformly distributed sphere, right? The mass distribution in this sphere is uniform, right? Inside it's proportional to r and outside is proportional to 1 by r square. Now let's talk about the acceleration due to gravity, right? Acceleration due to gravity. Now let's suppose acceleration due to gravity on the surface of Earth, right? On the surface of Earth. Now acceleration due to gravity on the surface of Earth. Let's suppose this is the Earth of radius r, right? And we are dropping a body very close to the surface of mass m, right? Of mass m, it's very close to the surface of Earth. Then the force acting on this mass m will be given by the Newton's law of gravitation. That's G capital M into small m upon r square, right? Because it's very close to the surface of Earth, right? Now this is the force acting on this mass m, right? If this is the force acting on this mass m, then this force will be equal to mass into acceleration, right? Mass into acceleration. Now acceleration here will be nothing, that will be equal to G m upon r square, right? The value of this gravitational constant is 6.67 into 10 to the power minus 11 Newton meter square per Newton meter square per kg square, right? And multiplied by the mass of Earth, that's 6 into 10 to the power 24 kgs upon the radius square. Radius of Earth is equal to 6,400 kilometers. That's 6,400 multiplied by the 1000, right? Whole square, right? Now, if you compute this value, right, we'll get this equal to 9.81 meter per second square, right? It will be approximately equal to 9.81 meter per second square. It means the acceleration due to gravity near the surface of Earth, it's a constant, right? It's a constant because there is not much variation in the height, so we can assume that the distance from the center of the Earth to the mass is equal to the radius of the sphere, right? So acceleration due to gravity in that case will be G, and that's equal to Gm by r square, right? That's equal to 9.8 meter per second square, and this value is on the surface, right? On the surface, or we can say near the surface of Earth. Near the surface of Earth. Now we can write this acceleration due to gravity in terms of density of Earth as well, right? Or density of any planet, right? It doesn't matter whether it's Earth or any planet, it can be any other planet as well, right? We can write the density or acceleration due to gravity as a function of density of planet or Earth, right? Now you can see here we got the value of G here as Gm by r square, right? Gm by r square, right? Density is nothing, it's equal to mass per unit volume, right? It's mass per unit volume, that's m upon 4 by 3 pi r cube, where r is the radius of the planet, right? So we can replace this m with 4 by 3, right? 4 by 3 pi rho into r cube, right? Right? 4 by 3 pi rho into r cube. Now substituting the value of m in this equation, the value of g will be 4 by 3 pi g rho multiplied by r cube upon r square, right? So this and this will get cancelled. We'll be left with 4 by 3 pi g rho r, right? So from here, in terms of the density, you can see the acceleration due to gravity. If the density of the planet is constant, density of the planet does not change, then the acceleration due to gravity will only depend upon the radius of Earth, and it will be radius of the planet. It will be proportional to the radius, provided density of the Earth is same, right? Provided the density of the planet is same, rho is constant, right? The rho is constant, then the acceleration due to gravity in terms of density will be 4 by 3 pi g rho r, right? So it will be proportional to the r, right? Now you can see in this question, there is a question on the screen. The density of a planet is double of density of Earth, right? And radius is 1.5 times that of Earth. The acceleration due to gravity on the surface of planet will be. Now you can see here the acceleration due to gravity on any planet is actually proportional to the density of that planet and radius of that planet, right? It's proportional to rho into r, right? Now, let's suppose for any planet P, so Gp upon Ge ratio will be actually equal to density of planet P and radius of planet P, right, upon the density of planet Earth multiplied with the radius of planet Earth, right? Now you can see here, density of planet is double that of Earth. So we can write rho P as 2s rho E, right? And the radius is 1.5 times the radius of Earth. So we can write it as 1.5 times Re, right? Upon rho E Re, right? So this will get cancelled, right? So it will be equal to 3, right? 3, right? It will be equal to 3. It means that the acceleration due to gravity on that planet will be 3 times, right? 3 times to the acceleration due to gravity on Earth, right? So it means it will be 3 times. So it will become 3 times, right, on that planet, right? So the acceleration due to gravity depends upon the density of the planet. It will depend on the radius of the planet as well, right? Now let's talk about the variation of the acceleration due to gravity with different heights, right? So the first variation will be discussed with respect to the variation in the height, right? Variation in the height. Now let's suppose we know that at different heights the force will be different, because at different heights the force will be different, because the Newton's second law equation says Newton's gravitation law of gravity says that force is inversely proportional to the square of the distance, right, between the two masses, right? So it means that as we increase the distance between the two masses, the force between them will decrease, right? If the force between them will decrease, then the net acceleration is going to decrease, right? So it means that if we try to calculate the acceleration due to gravity at some large height h, the acceleration will be less than that of the acceleration due to gravity on the surface, right? Let's suppose at some height h from the surface of this earth, there is a mass m. We have to calculate its acceleration, right? We have to calculate its acceleration. Now, its acceleration will be nothing. We know that the force acting on this mass m will be F, that will be equal to G capital M upon multiplied by M upon the distance. Okay, the total distance from this to this is nothing. It's equal to R plus H, right? It's equal to R plus H. So it will be R plus H ka whole square, right? That will be GM M upon R plus H ka whole square, right? So this is the net force, right? Therefore, the acceleration here will be equal to force upon mass, that will be equal to GMM upon R plus H whole square, right? So M and M will get cancelled. We'll be left with GM upon R plus H whole square. Now you can see here from this equation as well, the distance actually increases, right? If the distance increases, the acceleration due to gravity decreases, right? So it's decreasing, right? So it will be less than the value of G, right? Now, what we'll do is that we'll just take R square common from here, right? If we take R common from here, it will be R square outside 1 plus h upon r whole square, right? H upon r whole square. And we know the value of gm upon r square, that's nothing. That's the acceleration due to gravity on the surface, right? That is gs, right? Now replacing the value of gm by r square with gs, it will be gs upon 1 plus h upon r whole square, right? So this is the acceleration due to gravity at some height h. So this is the acceleration due to gravity at some height h. So at any height h, the acceleration due to gravity will be given by this equation, that's g upon 1 plus h upon r whole square, right? Now, let's suppose if h is small, right? If h is small, right? If h is small, if the height of this mass from the surface is small as compared to the radius of the earth, then we can approximate this equation like the a value will be equal to g multiplied by 1 plus h upon r. So we'll take it in numerator, right? It will be raised to power minus 2, right? We'll do the binomial approximation to it. So it will be g multiplied by 1 minus 2h upon r, right? 1 minus 2h upon r. So this is the approximate value at some height h, or at some, or we can say at smaller heights, right? At smaller heights. The value of gh is nothing. It's equal to g multiplied by 1 minus 2h upon r, right? Right? or we can say the change or the delta G here, that's equal to delta G here. Delta G will be G minus GH, right? That will be equal to 2H upon R, right? 2H upon R. So this will be the delta G here, or the change or the variation in the acceleration due to gravity at some height h will be given by 2H upon R, right? So this is the acceleration due to gravity for small height h, and this is the acceleration due to gravity for in general for height h, right? Now let's try to solve this problem, right? The question says that at which height from the surface of Earth due to gravity becomes 1/4 times of its value at Earth's surface, right? So we have to find the height, right? Height from the surface of Earth at which the acceleration due to gravity becomes 1/4, right? It means the value of GH is given here. The value of GH is given here. So GH value here is 1/4 times of as that of G, right? That's G upon 4. Now we can just write this equation. GH is equal to G upon 1 plus H upon R whole square, right? That's equal to G upon 4, right? G upon 4. G and G will get cancelled. So from here, 1 plus H upon R whole square, that will be equal to 4. Or 1 plus H upon R will be equal to 2, right? That will be equal to 2, right? So from here, H upon R will be equal to 1, or the height will be equal to the radius of Earth. So if the height is equal to the radius of Earth, then the acceleration due to gravity becomes 1/4, right? It will become 1/4. Now let's look at this second question. The value of acceleration due to gravity at a height 2r from the surface of Earth is, right? So the value of acceleration due to gravity at a height of 2r from the surface of Earth will be 1 plus h upon r whole square, right? I will just directly substitute the value of h here. So it will be g upon 1 plus 2r upon r whole square, right? So it will be g upon 9, right? G upon 9. So this will be the value of acceleration due to gravity at a height 2r, right? Towards the radius of Earth, right? Towards the radius of Earth. Now let's try to calculate the variation of acceleration due to gravity with depth, right? With depth, or we can say inside the Earth. Now let's look at this, right? Now let's suppose at some point P inside the Earth, at some point P inside the Earth, or we can say at a depth of T from the surface, right? There is a point P, right? Point P, and the radius of this Earth is R, right? There is a point P. At some point P, right, we have to calculate the acceleration due to gravity, right? We know inside the field intensity is actually proportional to the distance, right? So inside the field intensity is nothing, that's I is equal to G capital M into R upon R cube, right? So this is the intensity inside, right? Now the distance R from this point P to the Earth will be equal to R minus T, right? We can write here the value of R equal to R minus T, right? R minus T. So I will be equal to here Gm upon R cube, right? Multiplied by R minus T, right? Right? And this will be nothing. This will be the acceleration due to gravity, right? This is nothing. This is the acceleration due to gravity. So this will be the acceleration due to gravity, right? So G inside, we can write here, G inside will be equal to Gm upon R cube multiplied by R minus T, right? Now we know Gm by R square is equal to acceleration on the surface, right? That is Gs. So we can write here G inside equal to Gs upon R into R minus T, right? Or it can be written as Gs into 1 minus T upon R. So this is the acceleration due to gravity at a depth, right? So the change in acceleration due to gravity, right? Or we can say delta G value here, right? Delta G. Delta G will be here G inside minus G surface. That will be equal to minus d upon r, right? It will be minus d upon r. It means that as we move inside the surface of Earth, the acceleration due to gravity decreases, right? The acceleration due to gravity decreases. And as we move above the surface of Earth, the acceleration due to gravity will also decrease, right? So the maximum acceleration due to gravity will be at the surface of Earth, right? Now let's try to solve these questions, right? As well. So the question says that a body weighs 72 newtons on the surface of the Earth when it is taken to a depth equal to r by 2 from the surface of the Earth, where r is radius of Earth. It would weigh. It means we have to calculate the weight of this body at a depth r by 2 when the weight of this body at the surface is 72 newtons, right? So the solution of this question will be, we know weight is nothing, it's the mass multiplied by the acceleration due to gravity, right? It can be inside, it can be outside, it can be on the surface of Earth, right? Now, the acceleration due to gravity inside is nothing, it's equal to g into 1 minus d upon r, right? That's the acceleration due to gravity inside, right? Now, if you multiply by mass on both sides, what we'll get, it will be the weight, right? It will be the weight or the force. The force inside or weights inside, let's call that as W inside. And the weight on the surface of Earth is given as 72 newtons. Now at a depth of r by 2, so it will be equal to 1 minus 1 by 2, it will be half 72 upon 2, that will be equal to 36 newtons, right? So it means that the weight of the body will become half inside a depth of r by 2, right? The weight will become 36 newtons, right? It will be half of the weight on the surface of Earth. Now, the second question is that at what depth from the Earth's surface acceleration due to gravity is decreased by 2%, right? It's decreased by 2%. We know the acceleration due to gravity or inside the surface is g inside, that's 1 minus d upon r, right? Now the change in acceleration due to gravity is g inside minus g, right? That's equal to minus d upon r, right? Minus d upon r. That's our delta g, right? That's equal to minus d upon r. Correct. So that's the value of delta g. The value of delta g here will be g times d upon r. G times d upon r. It has to be g times d upon r here. And here also the value of delta g will be 2h g upon r, right? So this is the value of delta g. Now the percentage change will be nothing. It will be the delta g upon g multiplied by the 100, right? And the delta g is nothing. It's minus gd upon r, right? Upon g multiplied by the 100. G and G will get cancelled. It will be minus T upon R 200, right? Now the value is given as it actually decreased by 2%, right? So it will be 2%, right? That's equal to 2, right? This is given as 2. This is given as 2. Since it is decreased, we'll take it with the negative sign, right? So the percentage through which it decreases is given as 2%, right? Or we can say the depth here will be equal to r upon 50, right? R upon 50. So this will be the depth at which the acceleration due to gravity will decrease by 2%, right? Now let's look at this question. The question says, if the mass of the Earth increased by 2% and radius of the Earth decreased by 1%, then find the percentage change in g, right? The value of g is given by, that's gm by r square, right? So if the mass as well as the radius change, right, by delta m and delta r, then the percentage change in acceleration due to gravity will be delta g upon g, right? It will be delta m upon m, right? Plus 2 times delta r upon r, right? So this will be the percentage change in acceleration due to gravity, or the fractional change in acceleration due to gravity. So the percentage change will be delta g upon g multiplied by 100, right? This will be the percentage in change in g. That will be delta m upon m into 100, right? Plus twice delta R upon R, right? Into 100, right? So delta M upon M into 100, that's given as 2%, right? 2% plus, and the radius of the Earth decreased by 1%, so it will be 2 times 1, right? So the overall change in the acceleration due to gravity will be 4%, right? The 4% will be the net answer, or we can say the relative or the percentage change in acceleration due to gravity, right? This will be the total change in acceleration due to gravity, right? Or the percentage change in acceleration due to gravity, right? So let's talk about the gravitational potential, right? So gravitational potential is nothing, it's another way of determining the strength of the field, right, in a region, right? One way was to calculate the field intensity, another way is to calculate the gravitational potential, right? The gravitational potential is defined as amount of work done by external agent, right, required against the gravitational pull, right, in bringing a unit mass from infinity to that point without changing its kinetic energy, or we can say the mass will be in continuous equilibrium, right? It will be in continuous equilibrium, right? So that's the definition of the gravitational potential. It's actually the amount of work done by the external force against the gravitational pull, right, in bringing a unit mass from infinity to that point, right, without changing its kinetic energy. So it means that we are slowly and steadily bringing a unit mass from infinity against the gravitational pull, right, at that point. So this is what we call as the gravitational potential, right, for a unit mass, right? And in the same way, the amount of work done for mass m in order to bring that mass m from infinity to that point in a gravitational field is called as potential energy, right? So for unity mass, it will be a potential, right? And for total mass, the amount of work done will be equal to the potential energy of the system, right? So we'll be further discussing about the gravitational potential and the potential energy in the next lecture, right? We'll be deriving the potential for different mass distributions as well, right? We'll do that in the next lecture, right? So till then, take care and goodbye.